Hey everyone, welcome back to Daily Coding. Today's day 49. So I'm just going to look at a new problem here. We're greedy hand of straights. So I've never seen this one. You are given an integer array hand, where hand of I is the value written on the ith card, and an integer group size. Okay, so these are all the values of each card. You want to rearrange the cards into groups so that each group is of group size, and card values are increasing by 1. Return true if it's possible to rearrange the cards in this way, otherwise return false. Okay, so we basically have to take this array and divide it into subarrays where every subarray is an increasing sequence of group size. Okay, so right off the bat, nothing really comes to mind. So I guess the brute force solution would be generate all subarrays of length 4 of like length group size. So to do that, so what you could do is generate all subarrays of length 4. Well, first of all, you know that the length of hand has to be evenly divisible by 4 to be true. And if it's not, it must be false. So what you could do is generate all subarrays of length 4 and then check if each subarray is you could check if it's if they're all consecutively increasing by 1. Okay. So I thought of something else. So we know that so the group size is going to start with, so I'm wondering if I don't know if we could use a heap here or something, but we can what I'm thinking, maybe we can heapify these values in a separate data structure. And then we will take the minimum and then check so we know that there must be, so if we have a minimum n, it must be m plus 1, m plus 2, all the way to m plus group size. So this would be like our minimum value plus 1, minimum value plus 2. So in this case, our minimum value is 1, and then a 2 must exist in the dictionary, in the hand, or else the whole problem is false. Similarly, a 3 must exist and a 4 must exist. And all of these would get removed from the heap. Then we would pop from the heap again. So we'd have to remove these elements from the heap, and then we would pop from the heap again. And we would get 2 as our next minimum, and then we know we have to have a 3, have to have a 4, and have to have a 5. Also, we may be interested in sorting this list to get some information as well. Maybe we could do that instead of getting a heap. So if we sorted the list, that would be n log n. And then we could, so obviously if our array was like 1, 4, 2, 3, 5, 8, 7, 6, something like this, right? And we sort, so this is a case where it's all unique, is what I'm saying. Then when we sort it, we'll just get this. So in the case where our input is all unique, it becomes very easy to see whether or not it's a valid hand. The trick is, and this is true with the example when there's duplicates, so you could sort your array and maybe it would be like 1, 2, 3, 3, 4, 4, 5, 6. And this is also valid because you could do 1, 2, 3, 4, and then 3, 4, 5, 6. So, and I feel like this sort of input would be very easy to work with. So I think I could probably do an n-log-n solution. So let's, instead of doing this, let's try sorting our input. So if we have it sorted, we can go through the list. Okay, so maybe we can go through the list, and so there's two possibilities. So one, it's this number, so it's like I plus 1. Let's say a of I equals a of I plus 1 minus 1. So this number has to be exactly this number minus 1. Or a of I equals a of I plus 1. So this would be in this case where we have 2 3s. And then otherwise, if it's not either of these, so that means, so because it's sorted, we know that a of I has to be greater than or equal to a of I plus 1. Smaller than or equal to. If this is greater than 1, so if it jumps, for instance, from 1 to 4, then we know that the whole solution is false because there has to be a 2, 3, 4 here. So otherwise, it would be like the whole problem is false. So, okay, so this part is easy. And also to, let's say, if length of hand mod group size does not equal 0, then return false. So this just makes sure it's evenly divisible by group size. Okay, and then we'll sort hand. Okay, so when it is the same, so, okay, if we see, we may be able to just do like a math trick and be like, okay, we found one duplicate pair, so we can say like plus 1. And then here we found another duplicate pair, so we can say plus 1 again. So we'll have this sequence. Okay, but we also need to know, like, if this is 5, 5, 6, 7, that would be wrong. So we still need to make sure, okay, well, it would fail in this check right here because it says that it's different. So, okay, so here we have one duplicate and here we have another. So that means it's okay because we have two groups. So we can say number of groups equals hand divided by group size. So this will give us the number of groups. So the number of duplicates must be the same as the number of groups. That's my idea, because we can't just have one duplicate and have it be true. Because if we have one duplicate, 1, 2, 2, 3, 4, 5, 6, 7, 8, or it would just be 7, this would not work because we have 1, 2, 3, 4, and then this 2 has to jump to 5. Alternatively, if we had 1, 2, 3, 4, 4, 5, 6, this would also not work because we have 1, 2, 3, 4, and then 2 to 4. Okay, so my current algorithm would say this is true, but it's not. So we have to make sure that the pairs are also next to each other consecutively. Otherwise, in this case, so maybe I can code this for now, and then I'll run into this problem and figure out how to deal with it, where the number of pairs is not adjacent. Or sorry, the pairs are not adjacent. Okay, so we're going to sort it. Now we're going to say while I is less than length of hand, and we'll set I to 0. So if hand of I equals hand of I plus 1, so I guess we could say minus 1. While hand of I, so in this case, so I'll probably change the logic, but that means we're good to keep going. Otherwise, if hand of I equals, oh sorry, this should be minus 1. So this means it's stepping up by 1. Here, this means number of pairs plus equals 1. This is, let me just, I'll just do L if else. Well, I still want I to go up by 1 though. Yeah, so like that. L if else, so return false in this case. So here we're gonna do nothing. All right, so and then what would we return? We would return if num pairs equals num groups. Okay, so let's see this. I didn't try it on the example for list. Yep, we want length of hand. And the reason I'm doing this is just because if I run into any problems here, then I would like to know about it before I continue. Okay, we have an infinite loop. It's because we're not incrementing I here. So okay, I'll do this for now. Num pairs is not associated with a value. Num pairs equals 0. Okay, so we returned false, but the answer is true. Okay, so let's check this example out and see why it failed. I think I have an idea. It's probably because the group is something like 1, 2, 3, 4, and then 6, 7, 8, 9, and then when you get here, it fails. That's my guess. So let's see. 1, 2, 4, 2, 3, 5, 4, 2, 3, 5, 3, 4. Okay, so this gets sorted into 1, 2, 2, 3, 3, 4, 4, 5. Oh, this one actually works, huh? So we have 1, 2, 3, 4, 2, 3, 4, 5. Okay. So in this case, this changes. So it's actually returning false from here. But that is another case to consider if we have a jump. All right, so in this case, 2, 3, 4, 5. So maybe what I can do is I was thinking maybe I could use a hash map or something like that. So, okay, so we find 1 here, right? And then when we find a 2, that's good. When we find another 2, we say, okay, we have 1 unused 2. How many 2s do we have that are unused? We have 1. Okay, then we find a 3, which is part of our sequence, and then we go to 3. And now we say we have an unused 3. And then we go to 4. Okay, that's part of our sequence. And then 4. We have an unused 4 now. And then when we get to 5, we have to check, okay, do we have an unused 2, 3, and 4? So maybe a more efficient way, because that would be n. So maybe a more efficient way to store this information would be, instead of what we have, what we need. Sorry. So what I mean is, okay, so that's fine. We have 1 and 2. When we find, so we have an excess 2. So what that means is we need a 2. So, okay, so if we find an unused 2, that means we must have a 3, 4, and 5 to complete it. Okay, so then we find a 3. So there's 2 things we can do. We can pop here. Actually, this might be a really good way to do it in general. Okay, so we find a 1. So we find a 1. So that means we need a 2, 3, and a 4. Okay, so then we encounter a 2. So 2 is in our set, so we can pop it from the set or just remove it. Now we find another 2. So 2 is not in our set, so that means we have to start a new group. And this means we need a 3, 4, and a 5. So we can't really have a set. So maybe we should have a dictionary instead. So this solution would be n times group size. So my idea was, okay, so we have a 1, so that means we need 1, 2, 1, 3, and 1, 4. We find a 2, so because 2 is something that we need, we pop it. So this would go, we would decrement this value by 1, and then this, because it's 0, we would just remove it. All right, and then we find another 2. So this is not in our dictionary. So what that means is we need another 3, another 2, another 3, another 4, and we need a 5. Okay, then we find a 3, so we bring this down to 1. And then we find another 3. So that means this gets deleted. Then we find a 4, so this goes down to 1. Then we find another 4, so this goes down to 0, and we delete it. And then we find another 5, so this goes down to 1. So this looks really good to me. And I think it would actually work regardless of the order. So even if we had, let's say, 1, 2, and I don't even know if it has to be sorted anymore. So if we have 1, 2, 3, 4, and then 6, 7, 8, 9, when we encounter the 1, we would add 2, 3, 4 to our dictionary. When we encounter the 6, we'd add 7, 8, 9. So honestly, I don't even think it has to be sorted at this point. We could have it like this, and the same rule would still apply. So let's switch our method to this. I don't even know if we need that. Okay, so we're going to have cards needed, which is an empty dictionary. Okay, then we're going to loop through the hand. And we're going to say, so there's two cases. So if hand of I is not in cards needed, this means we need to add all of its everything to the dictionary. So we'll say for J in range, and we're going to go from starting at hand of I plus 1. So it's going to start at the next card, and we're going to go up until group size. Hand of I plus group size. So for instance, if we find a 2, we want to go from, and our group size is 4, we want to do 3, 4, 5. So we should be in range from 3 to 6. So 3 can be defined as hand of I plus 1, and this can be defined as hand of I plus group size. Okay, looks good. And what we want to do here is add all cards needed to dictionary. So if J is not in cards needed, so if it's not there, then we'll say cards needed of J equals 1. Otherwise, if it is in there, then we will decrement it by 1. Cards needed of J minus equals 1. So we'll bring down the count that is needed by 1, and then here we can just say if cards needed of J equals 0, then we can delete cards needed of J from the dictionary. We no longer need that card. Okay. All right, and then when we get to the end of this loop, of course we want to increment I by 1. And then when we're done, we'll return if, I guess we could say, if length of cards needed equals 0. Okay, let's see. I suspect I'll get an error somewhere, but let's see. I have the keyword is. Unexpected indent here. There. Okay, so I return true. Okay, let me see what cards needed is at the end here. Okay, so I'm never doing anything if it is. That makes sense. So if hand of I is in cards needed, wait. I don't think I need this part. I think my logic is incorrect. So, okay. So if we encounter a number and it is in there, then all we're going to do is just decrement it by 1. So we should do this part here. So we'll decrement it by 1 and delete it if necessary. Here, so this is, all we want to do is add all of its stuff. I don't think this actually goes there at all. All right, let's try that. Key error. Yeah. Okay, like this. And I don't know if we need it to be a while loop, like we might be able to use a for loop. Okay, here it says we need a 6. All right, let's see. Okay, so I just wasn't correctly adding it there. So let's see how this looks. This is supposed to be true. Okay, so here length is 2, so 2 mod 2 should be 0. So then this, and we don't ever use num groups. So when I encounter a 2, let me print out what it adds to the dictionary. So here I'll print cards needed. Oh, whoops, I forgot to use it as a test case. All right, let's run that. Okay, so it encounters 2, and because the group size, so that means it must need a 3. Oh, so maybe we do have to sort it. Because when it encounters 2, this could be part of, yeah, so I think we actually do need to sort it for this reason. Because I'm assuming that we need something greater than it, which is not necessarily true unless it's sorted. So I'll say hand.sort, and that should fix this one. Yeah. Okay, so I solved it. I'm not sure how slow this is. Okay, so this part is, so let's analyze it here. So this is n log n. I don't like how that looks. Okay, and so this is n log n. This part, so obviously it's minimum linear, but we're looping through group size times. Only if it's not in cards needed, because every time we loop through, so I guess the worst case would be what if we have, like, let's say our group size is let's say 4, and I have 1, then I have, so this would need 2, 3, 4, then I have 5, then I have this would need 6, 7, 8, then I had 9, right? So I just kept going up by 4 every time. 13, 17, 21. So this, with my current solution, would be the worst case, because it wouldn't, so it doesn't return false until all the way at the end. So we could do some jumps. We can jump out, because we know if we need a 2, right? If we need a 2, but we encounter a 5, then we know the solution must be false. So if hand of I is greater than, what if we also have a 3? Yeah, so if it's greater than any of these, if we encounter something that's greater than the last added one, then we know it's false. So I could make a variable here called last added and set it to j, and then I can say if hand of I is greater than last added, return false. So this means if we encounter something that's greater than the last thing that we added, we can return false. However, so that would work here, but what if we have 1, 2, 3, 4, and then we have 6, 7, 8, 9? So in this case, this is valid. This is a valid solution, right? So 1, we'd get 2, 3, 4, 2, 3, 4. When we'd encounter 2, we'd remove 2. When we encounter 3, we remove 3. When we encounter 4, we remove 4. So last added was still 4. Then when we go to 6, and maybe we should say, so and length of cards needed does not equal 0. So let's try that. And this might be last added is not associated. I don't know. Okay, so let's okay, so we could try both of these. So let me do it on LeetCode here. And I want to see where it ranks compared to other problems. So this one is called Hand of Straights. Hand of Straights. Okay, Hand of Straights. Code. Alright, so let's try this and see if it fails any test cases. Output limit exceeded. Okay. Do I have any other prints? No, just that one. Okay. Okay, looks pretty good. And what happens if I get rid of this clause right here? Does that, so we're at 37. Does it make a difference? Yeah. Yeah, it does. Okay. It's good to know. Yeah, perfect. So this is actually really important. Even though all it does is just exit the program prematurely, but I identified that our worst case looked like this. And then I realized, hey, we can actually just know right away. So I don't even know what our new worst case would be. Because we would, if we have, I guess our worst case is just a sorted list at this point. Because it will exit, like if we have 1 and then 5, it'll exit right away. So we can't have that. This would be like best case. So then our worst case would be if it actually has to go through the whole program, which in that case it would just be linear because it'll explore everything once. And then here it'll just add group size ones, but I don't think that really matters. So it's just nlog and to sort it, I think. So, all right, awesome. I'm glad I identified sorting would be useful here. I don't know if you have to do it that way. And then the dictionary, just kind of a very human way of thinking about it. Like, okay, I've encountered a 1, so that means I need 1, 2, 1, 3, and 1, 4, right? And then you just keep doing that, and then that way it allows you to be flexible. Like, okay, now I need 2 3s, for instance, because initially I had just the set, but then I realized, oh, hey, like I might need another 3 in my set, which is not possible. So usually when you find like, oh, I need duplicates in my set, but I still want O(1) lookup, then that's a great chance to use a dictionary. All right, great. So thank you guys so much for watching. Today was day 49, and I can't believe it, but tomorrow will be day 50 in a row. So thank you guys for watching, and I'll see you tomorrow for day 50.